We are now in C, where we will use the specific cumulant generating function from this exercise with the normally distributed increments to take a look at this Arfwedson approximation and try and see if it gives us something that is perhaps a better bound than that bound that we get in the infinite time Ruin estimate from the Lundberg inequality. So the first question we want to answer is which alpha yields the supremum of this g delta of alpha, where g delta of alpha is given as such, and we have our cumulant generating function from part A of the exercise. So part 1, we want to find the maximum of minus alpha minus delta multiplied by alpha plus alpha squared halves for alpha smaller than equal to minus r. So in order to do this, we calculate the derivative with respect to alpha. And that derivative is equal to minus 1 minus delta minus 2 multiplied by alpha divided by 2 multiplied by minus delta. So that is just minus delta alpha. And let's just set this equal to 0 and solve. That will imply that alpha delta is equal to minus 1 minus delta, which then implies that alpha is equal to minus 1 over delta minus 1. And now let's just make sure that this is indeed a maximum. Well, if we differentiate the derivative again, we see quite clearly that we get minus delta, which is a negative number. So since the second derivative is negative, we know that we have found a maximum value. So alpha equals to this maximizes our g delta of alpha. And then we're asked about when alpha is different from minus r. Well, first of all, let us just try to build in our constraint here that alpha is smaller than equal to minus r. So let's start by answering when is alpha smaller than equal to minus r. Well, that occurs when, well, we have to require this to be smaller than equal to minus r. So that means it must, if we multiply by a minus 1 on both sides, then that occurs when 1 over delta plus 1 is greater than r. And let us just recall, in this case, r is that value which, well, minus r is that value which sets this entire thing to 0. So in our case, r is equal to 2 because minus 2 gives a cumulant generating function value 0. So alpha is smaller than equal to minus r when 1 over delta plus 1 is strictly greater than 2, or similarly, when delta is then strictly, when delta is, well, it's not strictly, it's greater than equal, when delta is smaller than equal to 1. And we also know that alpha is strictly smaller than minus r, well, when 1 over delta plus 1 is strictly greater than r, which is 2, and that happens if and only delta is strictly smaller than 1. So now comes the cryptic question. When is alpha different from minus r? In this case, conclude that the Arfvedson approximation improves the infinite time Ruan estimate obtained by Lundberg's inequality. And one of the first things we might ask is, well, where does Lundberg's inequality come into play here? Let us just recall what we found out in B. In B, we found an expression for the finite time interval, for the finite, for the Rowan probability on a finite time horizon, which was given as the probability of Ruan on the time horizon 0 to delta u. And we found an upper bound for this, which was given by e to the minus u multiplied by g bar of delta, where g bar of delta in our case is this value maximized. Okay, so one thing that you can note is that when delta is equal to 1, we actually just have that the Ruan probability on the time horizon from 0 to u is bounded by e to the minus u multiplied by, well, whatever value we get when we plug delta equals to 1 inside here. And let's just try and calculate that, shall we? So on the side, let us just try to calculate the value of minus alpha minus delta alpha plus alpha squared halves when we plug in the optimal alpha. Well, how do we do that? Let's plug in the optimal alpha. Then we see that this is equal to minus 1 over delta minus 1. And now instead of plugging in alpha here and calculating, I just say minus delta alpha. That is equal to minus 1 minus delta, according to my calculation. So this term is equal to plus 1 plus delta. And then I have minus delta alpha multiplied by alpha halves. So what I have is plus 1 plus delta multiplied by alpha divided by 2. So multiplied by minus 1 over delta minus 1. And then I divide this by 2. Now if we go in and calculate all of this stuff, what you actually get is 1 plus delta halves plus 1 over 2 delta. And when you get this, this is the supremum of our g delta function, our g delta function for all deltas smaller than equal to 1. So that means if we choose delta equal to 1, then our Arfvedson approximation gives us, well, that the probability of Ruan before time u is equal to e to the minus u multiplied by 1 plus a half plus a half. So multiplied by 2. Now note that 2 is also our adjustment coefficient. So this thing here is actually our Lundberg inequality bound. The interesting thing now is what happens to this bound when I let d become strictly smaller than 1. What if d strictly smaller than 1? Which also means if alpha is different from r, as is asked in the exercise. Well, if d is strictly smaller than 1, then we need to figure out how this thing behaves for d strictly smaller than 1. And one way to do that is consider its derivative. This thing, when you try to differentiate it, well, the first term can just disappears, and then you have a 1/2 in both of these other terms, and you have 1 minus 1 over delta halves. And since delta has this as derivative. Now we note that delta, as we are considering it now, is definitely greater than 0, and right now we are considering it for delta smaller than, this is supposed to be a delta, sorry, for delta smaller than 1. Well, then I take 1 and divide by some number that is smaller than 1, then this term here becomes greater than 1. So it has this derivative, and the derivative is negative, which means that since 1 plus delta halves plus 1 over 2 delta has negative derivative on 0 to 1, it is greater than its value for delta equal to 1, so then it is greater than 2 for all delta in 0 to 1. And what this means then is that we now have that the probability of ruin on any finite time interval delta u, where delta is smaller than 1, well, that has an upward bound given by e to the minus u 1 plus delta halves plus 1 over 2 delta, which again is strictly smaller than e to the minus u multiplied by 2, which is the bound we get from the Lundberg inequality. So hence, when we constrict ourselves to a finite time interval instead of an infinite time interval, and one that finite time interval can be expressed as a fraction of our initial capital, well, then we actually have a better bound for the ruin probability on that finite time interval than what we get using the Lundberg inequality.